The most important feature with respect to Cortex M3 and M4 processor is nested vector interrupt controller. As we see here, all the interrupts are controlled with the help of nested vector interrupt controller, which is present inside the architecture of Cortex M3 and processor, Cortex M3 and Cortex M4 processor as shown here. The nested vector interrupt controller is a part of Cortex M processor. It is programmable and its registers are located in the system control space of the memory map. The nested vector interrupt controller handles the exceptions and interrupt configurations, prioritization and interrupt masking. The NVIC has the following features. There are 4 features with respect to nested vector interrupt controller, among which the first one is flexible exception and interrupt management. Second one is nested exception or interrupt support. Third one is vectored exception or interrupt entry, and the fourth one is interrupt masking. Let us see one by one. The first one, flexible exception and interrupt management. Each interrupt apart from the non-maskable interrupt can be enabled or disabled and can have its pending status set or cleared by the software. The nested vector interrupt controller can handle various types of interrupt sources. Pulsed interrupt request means falling edge and rising edge is called as pulsed interrupt request here. The interrupt request is at least 1 clock cycle long. When the nested vector interrupt controller receives the pulse at its interrupt input, the pending status is set and held until the interrupt gets serviced. Pulsed interrupt request means what? Edge triggered interrupt, what we see in our 8051. So there is a falling edge and rising edge, or both edges can be detected as per the convenience, as per the requirement. So which is called as pulsed interrupt request here. And level triggered interrupts is normal, like we do level triggered interrupt in 8051. So the interrupt sources holds the request high until the interrupt is serviced. So various types of interrupt sources means edge triggered interrupt and level triggered interrupt. The same way in an ARM processor architecture it is called as pulsed interrupt request and level triggered interrupt request in ARM environment. The signal level at the nested vector interrupt controller is active high. However, the actual external interrupt input on the microcontroller could be designed differently and is converted to an active high signal level by the on-chip logic. Nested interrupt support or nested exception support is the second feature, where each exception has a priority level. As external interrupt 0 is having highest priority, serial interrupt is having lowest priority, everything has some priority level, every interrupt has some priority level. Some exceptions such as interrupts have the programmable priority levels and some others have a fixed priority level. When an exception occurs, the nested vector interrupt controller will compare the priority level of this exception to the current level. If the new exception has the higher priority, current running task will be suspended. Some of the registers will be stored in the stack memory and the processor will start executing the exception handler of the new exception. This process is called as preemption. This mechanism allows nesting of exception service without any software overhead. Third feature is vectored interrupt entry. When an exception occurs, the processor will need to locate a starting point of the corresponding exception handler. Traditionally, in ARM processors such as the ARM TDMI software handles this step. The Cortex M processors automatically locate the starting point of the exception handler from the vector table in the memory. As a result, the delays from the start of the exception to the execution of the exception handlers are reduced. And the fourth feature is interrupt masking. Nested vector interrupt controller in the Cortex M3 and Cortex M4 processors provide several interrupt masking registers such as primary mask result register. Using the primary mask register, we can disable all exceptions including the hard fault and non-maskable interrupt. This masking is useful for operations that should not be interrupted, like time critical control tasks or real-time multimedia codecs. Alternatively, we can also use the base priority register to select the mask exceptions or interrupts which are below a certain priority level. And there is a vector table. When an exception event takes place and is accepted by the processor core, the corresponding exception handler is executed. To determine the starting address of the exception handler, the vector table mechanism is used. Vector table is an array of word data inside the system memory, each representing the starting address of one exception type. Vector table is relocatable and the relocation is controlled by the programmable register in the nested vector interrupt controller called the vector table offset register. After reset, the vector table offset register is reset to 0. Therefore, the vector table is located at the address 0 after reset. For example, if the reset is exception type 1, address of the reset vector is 1 times 4. Each word is 4 bytes, which equals 00000004, and the non-maskable interrupt vector, which is type 2 interrupt, is located at the vector location 00000008. The address 0x00000000 is used to store the starting value of the main stack pointer. The least significant bit of each exception vector indicates whether the exception is to be executed in the thumb state. Since the Cortex M processors can support only thumb instruction, the least significant bit of all the exception vectors should be set to 1. So this is the vector table, exception with the exception number, the corresponding type, and the priority. Here you see there are exception numbers like exception 1, 2, 3, 4, 5, 6, 7, 8 up to 255. So there are 255 exceptions with the number 1 to 255 as we see here, out of which the exception number 1 is the highest priority, which is reset, and its priority is given as -3, and exception 2 is non-maskable interrupt, and its priority level is -2, and exception 3 is the hardware fault exception, and its priority is -1. So reset, non-maskable interrupt, and hard fault are the 3 exceptions which are having the fixed priority levels as -3, -2 and -1 as we see in this table. From the 4th exception number to 255 exception number, all are programmable. All exceptions priorities are programmable as we see here. So memory management fault, bus fault and usage fault are programmable, and supervisor call, debug monitor, pendable request, and the system tick timer and all other interrupt requests are programmable. So there are fixed priority for reset, non-maskable interrupt and hard fault. Among these 3, reset is having highest priority than non-maskable interrupt. Non-maskable interrupt is having highest priority than hard fault. Next to these 3, all other interrupts from 4 to 255 all are programmable as we see in this table very clearly. The another table gives the vector location. Here we see where initial value of MPS. In this book in 4.26 it is given as MPS. There is nothing like MPS. It is main stack pointer. Okay, so it is main stack pointer MSP. Okay, so at reset, the program execution at the reset, the address is 00, the offset is 00, byte offset is 00. So the initial value of main stack pointer should be stored in this 00, and the reset is having the offset as 4, and non-maskable interrupt is having the offset as 8, and hard fault is having the offset as C, and the memory management fault is having the offset as 10, and bus fault is having as offset as 14, and usage fault is having the offset as 18. Main program starts at 04, and non-maskable interrupt starting address is 08, something like this. Here you can write the jump instruction, and you can use the corresponding hard fault service routine or reset routine or non-maskable interrupt service routine, etc. as per the requirement of the applications. So here it is exception type 1, 2, 3, 4, 5, 6 up to 255 and the corresponding offset. So in the previous table 4.25 we have seen the 4.9 we have seen the exception priorities, and here it is we are able to see the vector address offset as we see here. Okay, so and finally the fault handling. Several types of exceptions in the Cortex M3 and Cortex M4 processors are fault handling exceptions. Fault exceptions are triggered when the processor detects an error such as the execution of an undefined instruction, or when the bus system returns an error response to a memory access. So the fault exception mechanisms allows errors to be detected quickly and potentially allows the software to carry out the remedial actions as shown in the figure 4.27. So hard fault exceptions, whenever there is a fault happens, it can trigger the debug during software development, and error handling in software, error reporting can be done just like that by using this. By default, the bus fault, usage fault and memory management faults are disabled, and all fault events trigger the hard fault exception. However, the configurations are programmable, and when we can enable the 3 programmable fault exceptions individually to handle different types of faults. The hard fault exceptions is always enabled. Fault exceptions can also be useful for debugging software issues. For example, the fault handler can automatically collect information and report to the user or other systems that an error has occurred and provide debug information. Number of fault status registers are available in the Cortex M3 and Cortex M4 processors, which provide hints about the error sources. Software developers can also examine these fault status registers using the debugger during the software development. And these are all the references. And thank you.